So good afternoon, guys. Thank you for making it during the lunchtime. We really appreciate it. So, during Next, we've been hearing all about powerful foundational models and agentic systems for AI. So that's not what this talk is about. This talk, we're going to talk about how you build the infrastructure to basically train and serve these agentic AI systems. Right? So we'll cover three things in this talk today. Why are we building this large infrastructure? What is this? What are rack scale systems? And the third one is we're going to talk about how do we, Google Cloud, build and deploy these rack scale systems and make it available to our customers. So my name is Pramod, and I'm joined by Manish, and we are both product managers in the GPU team. So we work on building and deploying rack scale systems on Google Cloud. And I'm really excited to have Deepak as well. So he's a senior research scientist at Nvidia. He's going to talk about how Nvidia uses these rack scale systems to build their foundational models today. It's pretty exciting. So since 2025, Google, we've been working on building and deploying GPU rack scale systems. And we've already delivered thousands of GPUs to our customers today. We started with the A4X using the GB300 NVL72 system. So this is an exascale platform. So it connects 72 GPUs via an NVLink backplane that allows all the 72 GPUs to get interconnected with high-speed NVLink in a single rack. And we followed that up last year with the A4X Max using the GB300 NVL72 system. And then we'll continue that journey on with the Vera Rubin platform with the A5X machine series as well. So these systems are being built for all the new foundational models today. Now coming to that, why even bother building these large scale systems, right? So we see two trends in the ecosystem today. So one is models are getting larger. We see 10x growth in the number of parameters, longer sequence length, context lengths for inferencing. And the second thing is new scaling dimensions. Last year it was all about test time scaling, where inference required a lot of compute for throughput and latency, but we are seeing a new scaling dimension in agentic AI, right? So all of these workloads require a lot of compute and also good latency, because you want answers as quickly as possible. So at Google, we follow sort of this approach to building GPU-optimized infra. So we start with compute, combine that with large-scale networking fabrics to build really large GPU clusters. And then we combine that with high-speed, high-performance storage solutions across block, file, object, to cover a gamut of ML use cases. But you might ask, what does that actually mean in practice? So I want to share a vision slide with you on hardware-software co-design. So you can see in the first column here, we're working on building very high-density compute systems, starting with the A4X, continuing on to very large and high compute density systems that span 576 GPUs that are connected with NVLink. Now, these high-density compute systems bring sort of two challenges, right? One is power delivery. So these racks are getting to almost 1 megawatt per rack. So we are redesigning our power delivery systems within Google data centers to power these racks. The second thing is about thermal management, right? So as you get to high-density compute, how do you cool these systems? So we're at Google, we're leveraging our third-generation CDU row-level cooling technology. We've been deploying these at scale for the last, I would say, 9 years. Since the TPUs, we're bringing that to our GPU rack scale families. And then, in 2027, we'll go to our 5th generation. So we contributed the Deschutes project to the OCP community last year. So we're continuing along that journey with liquid cooling. And then, we're also working on large-scale networking fabrics. So, last year, we were all focused on building really large non-blocking clusters in a single data center building. And then we scale that out with the Virgo fabric, encompassing multiple data center sites to create really, really large, GPU compute clusters. And also we combine that with a lot of networking software, right? So whether that's optimizing GPU collectives with Nickel, Nixel, and all the different communication libraries, And also things like load balancing. How do we scale out? Like as workloads scale to thousands of GPUs, we need to scale our Rocky RDMA fabric and make that high performance. And finally, we are actually building supercomputers in the cloud, right, with these rack scale systems. So the question is, what kind of software do we build to make these systems resilient and performant as possible, and also make them operable at scale, right, with a single pane of glass. And that's what the whole cluster director effort is. So now that we we covered the why are we building these systems, let's look at what are these systems. So this is a picture of the A4X Max, the GB300 system. So it is a OCP compliant rack. We build an industry standards rack which combines 18 servers and 9 switches in a single rack, all connected with an NVLink cable backplane that connects all the B300 GPUs together. And we also scale out using CX8s with a 8-rail optimized design. And then we also have a new data center scaling that allows us to combine multiple sites into creating a very large GPU non-blocking cluster. And with all of this compute, then we can train really large foundation models. We can target model serving use cases, especially as these systems become long context, longer sequence length. And then I also want to point out that these systems are really good for general high performance scientific computing use cases, right? So because you get coherent memory, you get different precision type support, and you also get the NVLink interconnect. So it's really targeted a variety of different high performance accelerated computing use cases. So let's take a small digression into, a deep dive into what the single node looks like. So each of these compute servers, these 18 servers in the rack, this is what a diagram looks like. So it's got 2 Grace CPUs connected with 4 B300s and the CX8 NICs for scale out. So the 2 things I want to call out in this slide is that the B300 is connected to the Grace CPU using NVLink, and this forms like a coherent memory fabric. And this means that it's a simplified programming model for programmers, right? So you can use standard malloc free in order to do memory transfers between the CPU and the GPU. And because it's NV-linked, then you can go 3.5x faster compared to PCIe, right? So you get pretty high interconnect bandwidth. And the 4 B300s are connected to the NVLink switch fabric, as you can see in the yellow bar there. So as you expand up to the full rack, then this is what a full rack looks like with 18 nodes. And then this means that now since you have the NVLink fabric, one B300 on one node can talk to another B300 on a completely different node within the NVLink, within the rack, and exchange memory, right? So now your models can scale up to almost 21 terabytes of memory, right? Because the entire GPU memory is accessible to all GPUs. So you can basically program all of these GPUs as one large, gigantic GPU. So looking at scale out, so what we do is we then build a 3-tier fabric by connecting multiples of these racks together, and then connect them to our Jupyter optical circuit switch, and we build really large non-blocking clusters with rail optimization. So this allows traffic to flow in a low latency manner from one GPU to the next. We also do a lot of optimizations as far as load balancing is concerned. We optimize GPU collectives, and we ensure that all traffic is segregated. Like GPU traffic shouldn't interfere with compute and storage. So we make sure that GPU collectives are as fast as possible. So with that, I'm going to hand it to Manish to talk about what are we building next. Right? I talked about Grace Blackwell today, but he's going to talk about the future.
Thanks, Pramod. So having discussed what we are deploying today, I just wanted to give you a quick peek of how we are thinking about these systems going forward. So this is a preview of our Nvidia Vera Rubin NVLink-72 system that we are actively working on. Vera Rubin is set to redefine the AI performance, but to truly harness its power, we need to design these systems from grounds up. And that's what we have been working on in Google Cloud to bring this system to production later this year. It's a deep co-engineering collaboration that combines the Vera Rubin performance with the Google innovation in various different dimensions. One, networking. So we are bringing a brand new innovation of Virgo networking that I'm going to dive deeper in a minute. We combine that with advanced cooling systems that Pramod talked about. So this system is going to use the 4th generation advanced cooling that's innovated at Google. And then these systems are seamlessly integrated with our AI hyper architecture and software systems like Cluster Director, so that the management of these systems is easy. So just to dive down a little deeper into the system aspects, at the compute at rack level, the system is going to deliver up to 3.5x increase in flops for both training and serving purposes. It's going to deliver up to 3x memory bandwidth increase compared to GB200. That applies to, again, a wide dimension of workloads, and total collective of around 21 terabyte of high bandwidth memory. In addition to that, the networking allows the new networking fabric will allow us to scale to tens of thousands of GPUs with a non-blocking RDMA fabric. This is also integrating our the cluster director services, which means that you get a unified plane, whether you're running your systems through Vertex, Cloud Run, GKE, you get the same A5X bare metal performance for the maximum applicability for your workloads. So just to click down on the networking, as I mentioned earlier, that hardware on the GPU side is one aspect. Then we focus on how can we make the networking not be a bottleneck to scale for tens of thousands of GPUs. So the Virgo network is a new mega scale out fabric designed for the extreme requirements of the modern AI workloads. And this is basically the engine of the AI hypercomputer. And by leveraging high radix switches, we are able to collapse the network into a flat 2-layer network non-blocking topology, which directly impacts the latency and the number of tiers the packet has to traverse. And as shown towards the top of the picture over here, the Virgo network deploys a multi-planar design with independent control domains. So what that does is that it ensures that the network is not just fast, but is also resilient, containing the fault domain to a single plane. Virgo is expandable to multiple data center sites. So at any given one data center site, you can scale up to 80,000 GPUs. And then when you mesh the number of other data center sites, it can go up to more than 900K GPUs. The other aspect of Virgo is that we're making sure that the data that feeds into these cluster is not a bottleneck. So Virgo network coexists with Jupyter, which is the state-of-art of Google's front-end network that allows us to make sure that you have the GPUs have the access to the storage as well as the global WAN that is as fast and reliable as the Virgo network itself. So we covered the system, we covered the networking, and next is the storage. The storage, like in today's massive AI models, require a storage infrastructure that needs to scale at unprecedented scale and speed. At Google Cloud, like we are focusing on engineering our storage solutions to make sure that the data is not the bottleneck and making sure that your valuable GPU resources are always productive. So one of the storage services that we are very proud of is the Google Cloud Storage. It is the backbone for your AI data lake, designed to effortlessly scale to exabytes. You can have your training pipelines in those data sets. You can have processed features, or you can have model archives. So GCS can hold it all. The other element of the GCS is the rapid cache. Rapid cache is a high-performance zonal service as part of the GCS storage umbrella that brings data closer to you for low latency and high throughput use cases. So one of the common things we have heard from our customers is that there is often they face a cold start problem when they're trying to spin up large training clusters. So with rapid cache, we have seen up to 2.2x performance for the checkpoint restore time when they're trying to use rapid cache instead of loading it from the remote storage. The other benefit we have heard is the low latency inference use cases. So depending upon where your customers are, your data may reside at one common place, but you can bring the KV cache solution closer to the zones where you're serving your customers from. And this can deliver up to 2.5 terabytes per second of bandwidth for those use cases. Now, in addition to that, there are systems that from the legacy reasons or the dependency, they use POSIX file system. We also provide flexibility to use or mount the GCS object storage bucket as file using GCS Fuse. So that's all under the GCS umbrella. Now, for the shared storage, we offer the managed lustre. We recently announced earlier at Next that now we can scale up to 10 terabytes per second of bandwidth. This is helpful for training your large data sets as well as for shared scratch space where you need to read simultaneously from a lot of storage nodes. And then we also work with customers across the board that want to deploy their own storage solutions. So for that, we offer our storage optimized VMs as part of our Z family compute instances, where you can bring your own storage stack, and that are also compatible with the RDMA fabric, so that you don't have any bottlenecks, even if you want more granular control on your storage architecture. And that's what I meant by giving more flexibility and removing any bottlenecks that you typically incur in the data-intensive AI applications. So we are going to support GPU direct storage or leverage GPU direct storage for both our managed services as well as for the SOVM-based deployments, where you are deploying your own storage stack on the Z family of products. They can communicate with their GPU cluster over RDMA using GPU direct storage. A lot of these GPUs are provisioned with the local SSDs. So even if you're reading from the node local SSD of the GPU, we can use the GPU direct to load it without bringing the CPU into the picture. So it reduces the CPU overhead and reduces the latency overall. I'm going to hand it back to Pramod to talk about how do we optimize some of these rack scale systems. This was about what the capabilities are. Now we are going to talk about optimizing.
Yep. Great. So we talked about the why and the what, but we'll continue the what just a few more minutes here. So we've talked about rack scale systems, but what are these systems good for in terms of like what optimizations do they enable, right? So we'll cover that in a few slides here. So when you first start model training, one of the first things that you'll do is you'll try to scale out using data parallelism. So in this case, it's FSDP. So the NVLink-72, which you have 72 GPUs connected with the high-speed interconnect, allows you, accelerates all the the primitives that we use with FSDP, which is all gather, all reduce, all scatter. So by leveraging the NVLink bandwidth, you can just make scaling out much easier, right, from a data parallelism point of view. And this sort of extends to tensor parallelism as well, because TP. So I have a small code snippet here that from PyTorch it's setting up the TP size to 4, because once you, like with traditional 8 GPU systems, once you start exceeding TP equals 8, you start going to the DC bandwidth, and then it becomes really slow. Like tensor parallelism gets really slow. But with 72 GPUs, you don't have to worry about limiting your tensor parallelism size to 8 anymore, right? You can scale out beyond 8. And it also, that also enables more parallelism strategies. So, these days, when you're doing model training, you're sort of combining almost like, 4 to 6 dimension parallelism here with, pipeline parallelism. You go to expert parallelism as models get sparser with mixture of experts architecture, which, Deepak is going to cover a little bit more in detail. And then you can also do sequence parallelism. So basically, all of these different sorts of parallelism strategies involve different communication primitives. And what we're trying to say here is that with the 72 GPUs that are interconnected, you can basically accelerate all the different types of collectives. And with even optimizations like the NVLink switch reductions, you can do all reduce can be offloaded onto the switches, so you can get much faster from a GPU communication bandwidth. So, so we talked about scaling out strategies. Now, if you remember, the CPU and the GPU were also connected with NVLink, and what that does is it enables more like scaling up optimizations as well, right? So one thing you can think about is how do I offload, my model state. So this could include things like the KV cache, for example, which can be now distributed across 18 machines across the 72 GPUs. You can offload your checkpointing or model states to the Grace CPU. Now that frees up the GPU memory for you to do more computation and communication. And then we worked with NVIDIA to upstream a lot of the different APIs. So these are known as memory pool APIs in PyTorch and JAX. That basically allows you to to access all of the unified memory that you get with the NVLink system, and you can basically use these APIs to access the memory pool very, very quickly. And then finally, another scale-up optimization that can be enabled with Blackwell GPUs is essentially the transformer engine with FP4. So as you get these systems to do inferencing, for example, you can use lower precision to accelerate the throughput of your inferencing and get better flops. The GB300 has a lot of FP4 flops with new tensor cores, so you can get access to all of those with the lower precision types. Okay, so now we covered the why and the what, and then I'll hand it back to Manish to cover like how are we deploying these systems and making them available easily on Google Cloud.
Thanks, Pramod. So deploying these clusters, just a quick raise of hand, like is anyone in the room already deploying some of these systems? Awesome. And are there any on the fence that they want to deploy, but they're concerned about, like these are large scale systems, the management part of it? Cool, that makes my life easier, like not concerned about that. From the management perspective, I think we want to give you a quick gist of like making sure that the issues that the customers typically run into when they're deploying these large-scale clusters are part of our design philosophy from day one. So number one is how do you provision this large-scale capacities? And as you understand in the industry, there is a supply-demand issue with the GPUs. So we want to give as much flexibility to our customers to make sure that they can get access when their workload demands it. So from the capacity consumption model, we offer reservations up to several years so that you can have a guarantee that when you have the access to these systems when you really need it. But not all workloads need long-term reservations. So for that, we offer a solution called Dynamic Workload Scheduler. The Dynamic Workload Scheduler has two flavors to it. One is the Flex Start mode, which is designed to make sure that you can get the capacity over a certain prescribed days that you want over. So let's say you say, I want this capacity over 7 days. The system will make sure that within the span of those 7 days, you get that capacity. So that's the flex mode. Calendar mode is something like similar to hotel reservation, where you need more higher predictability than the on-demand. So you can prescribe when do you want that capacity over a span of 90 days. So that's for the capacity aspect of it. Now, once you have the capacity, how do you provision some of these clusters? So one is that we want to make sure that you have access to the other key components of your system. So high performance storage options, whether it's GCS Rapid that we talked about, or managed clusters, are integrated within the clusters. We offer one-click deploy for the out-of-box support for the most popular orchestrators, whether it's GKE that you are using or Slurm. That includes the support of the native IMEX integration for the NVLink fabric. And the schedulers within these orchestrators are fully aware of the underlying physical topology. The physical topology is going to play more and more important role as we scale the workloads to make sure that the inter-GPU communication and the bandwidth is not a bottleneck. And that's what the topology of our schedulers do to make sure that your workload is placed where it's needed. So there are two layers for your the capability that we offer for your infrastructure journey. I mean, the intent is that you spend your time training your models and not managing the infrastructure. And to solve this, we approach the problem with two complementary layers. are designed to meet your engineering teams where they are. So one is the cluster toolkit. This is a highly customizable open source foundation that gives you incredibly reliable, repeatable way to build your infrastructure. An example is that we'll give you certain recipes as a guide that you can look at, or you can build your own recipes and make a Terraform script that can be version controlled and run to produce the same results. Second, we have Cluster Director. This is a fully managed lifecycle environment, which sits directly on top of the toolkit functionality. There's nothing absolutely wrong using the toolkit. It simply comes down to how much control you want to give to us for managing your infrastructure. So the way I want you to think about the Cluster Director is that it's a managed lifecycle with the unified control plane that allows you to provision, validate, scale, and operate. By provisioning, we mean that you're not starting from scratch. We give you a guided path so that you get to a sane, high-performing cluster to begin with. Then validate means that you are increasing your confidence before you burn your expensive hours on training. And then the scale means that you can move beyond the fixed fleet. You can scale based on the demand. And then operate means that you need to get the visibility. We give you the dashboard, health workflows, repair guidance, and then the governance signals you need to keep your workload running. Pramod mentioned that, and I'm again going to highlight the topology-aware scheduling is becoming more and more critical. So we offer the topology-aware scheduling whether you're using GKE or Slurm. So GKE auto-configures the NVLink setup and can set up the pools per NVLink domain. So leveraging Kubernetes dynamic resource allocator, it schedules the training and the inference job fully aware of the underlying NVLink topology. And for Slurm users, our integration leverages the block plugin. The version is mentioned there. You can define the block of nodes like NVLink-72 domain in the configuration, and the hierarchy that you need that respects the data locality. So this ensures that the communication-intensive parts of the workloads can run with the highest bandwidth domains. So a quick glimpse of what we are doing on the GKE. So GKE, I mentioned the dynamic resource allocator handles the NVLink fabric setup and topology awareness. In addition to that, we are now making networking as a first-class recipient to make sure that the networking is also factored in as part of your setting up the cluster. So accelerated network profile automates the provisioning of VPCs, subnets, IP ranges, and the RDMA NICs ensuring that the network is optimally configured. So as part of the managed DRA net, we treat RDMA network interfaces as first-class schedulable resources within the Kubernetes. So this allows the fine-grained control for the network optimized AI workloads. And then you've got everything set up, it's running. Now you want to make sure that you have the transparency and the observability as to how things are running. So as part of our day 2 operations, we provide a comprehensive full-stack telemetry that goes beyond the standard GPU. So you have GPUs telemetry, NVLink telemetry, storage telemetry, DCN fabric telemetry. So this is accessible via APIs and visualized in customizable dashboards. We also provide tools for analyzing the nickel communication to make sure that the slow nodes or the straggler nodes can be easily detected. The heat map on the right over here kind of shows that the system is detecting that there is a straggler that has started showing up in your system, and that straggler can then, that effect can cascade down to the rest of the clusters. So the goal is to detect those early so that we can then do a repair on them. We also provide playbooks to help troubleshoot some of the common issues so that you have a starting point if you're doing it on your own. And then finally, the resiliency is again paramount for these large running AI jobs. So we offer cluster health checks. These cluster health checks are constantly running on the active nodes, on the passive nodes, and making sure that with the roads, when they are repaired and are being brought back to the systems, there's a healthy checks that are done before that. So we offer APIs for you also to report and repair APIs for the problems that you may see in the NVLink fabric, so for the swift diagnosis and the remediation. So this is critical functionality that we want to emphasize that is becoming more and more important, specifically for the rack scale systems. And these are built in as part of the integration that we are doing. And then the customers also want more control on the maintenance, at what maintenance windows they want these maintenance events to happen, and when does the repair needs to happen. So we are offering, as part of the Cluster Director, emergent APIs that allows you to prescribe your window when these management and repairs can be done. So putting it all together as part of the overall cluster, we have integrated, like I'm going to give an example of inference, like how it all comes together, the routing, scheduling, and storage into a single stack. So your engineering teams don't have to build and maintain this infrastructure themselves. So on the left-hand side of the picture, we are showing that intelligent routing. So the GKE inference gateway is a capability that allows, and the LLMD optimizations plugin that are part of that, allows you, the system, to have an understanding of where the model, what the model internal state is. So it can look at the KV cache across your cluster and sends the incoming request directly to those specific pod that already hold the relevant context. Because the standard load balancers based on the basic metrics don't work for these systems or will not be efficient. And to support the inference workloads, as I mentioned earlier, the standard inference VLLM frameworks are deployed natively on GKE. In addition to that, the dynamic workload scheduler that we talked about, that gives you the flexibility for the node recycling for transition time. So you can start with reservations. Dynamic workload scheduler will proactively provision a new node so that there is a node available before it decommissions the old one. So you can fall back from reservations to the DWS to spot instances, so that there is no break in your the workload deployment. And then on the right is the storage part that is integrated with the GKE. So you can have the rapid cache, managed cluster, or bring your own storage as part of that. So there are a few talks happening at Next that I'll encourage you to learn even more what's happening in the GKE. And finally, on the AI hypercomputer side, like we have been discussing, I mean, the whole purpose is to power some of the most demanding AI workloads in the world, from foundational model training to the cutting edge AI product development. So let's look at some examples. So the number one is the DGX Cloud. So this is a fantastic example of our collaboration with Nvidia. The DGX Cloud is hosted on Google Cloud and provides a fully managed AI supercomputing environment. This is leveraged by Nvidia to build and operate their internal research and develop next generation models. And this is running on Google A4X infrastructure that Pramod talked about. OpenAI, as a leader in research and development, is building and scaling their foundational models on these NVLink-72 systems. And then Thinking Machine, this is the research and product company, the creators of Tinker, for the low rank adoption fine-tuning models that are using the GKE clusters, GCS services, and the rapid cache to be as performant as possible on the NVLink-72 systems that we deploy. So with that, I'll invite Deepak to talk about how NVIDIA is looking at these systems and how they are thinking about optimizing it for the future LLM models.
Cool. Thanks a lot, Manish. So hi, everyone. I'm Deepak. I'm part of the Applied Deep Learning Research Group at NVIDIA. Among other things, we build the Nemotron series of models. And today I'm going to be talking a little bit about how NVIDIA uses NVL72 to build models. So today's LLMs are largely driven on top of the mixture of expert model architecture, where really briefly, you have a gating network that decides what subset of experts should be used for each token in your input. And a common design pattern for these MOEs is to have each token go to a fixed number of experts. So you might have n total experts, and your MOE routes each token to k of those n experts. So this is a figure showing the publicly released MOE models over the last 2.5 years or so. Time is on the x-axis. Number of experts in the model is on the y-axis. And I've color-coded the number of experts each token is going to, the top k routing factor, in different colors, right? And so you can see some pretty interesting trends going from left to right. You can see that the number of experts in these models is increasing. And you can also see that this top k routing factor is also increasing over the last year or so. Right? So this trend has profound effects on training speed. So as models become more granular, the underlying gems that you need to execute in model forward and backward passes become smaller. And so it's more challenging to execute them efficiently on modern accelerators. And so one way of kind of routing around this issue is to use expert parallelism, which Pramod talked about earlier today. Briefly, with expert parallelism, what you're doing is you're trying to collect more work on each GPU for a particular expert. So you shard your experts across the different GPUs, and then you kind of do a distributed permutation to ensure that all the tokens that are routed to a particular expert go to a single GPU. And this makes the gems on that GPU larger and more efficient to run. But this doesn't come for free. You need to pay some communication cost to actually route the tokens to the GPU that have the experts that are going to be executed for those tokens. And this communication cost scales roughly with top K, right? So if you're training a model that has higher top K, then there's more communication associated. And so larger NVLink domains really help ameliorate this extra communication overhead that comes from deploying expert parallelism for these quite granular MOE models. And then also, as you might have seen on the previous slide, the number of experts is increasing. That means that the total number of parameters in a model are increasing for the same active parameter count. And so when we're training these models, we need to have enough GPU memory to keep around the model parameters and the optimizer state and the intermediate activations. And this can become quite challenging. And so we're forced to use more communication-intensive parallelism techniques like FSDP that give us the ability to shard all three of those different types of state across all of the GPUs being used for training. FSDP is more communication-intensive, and so larger NVLink domains like NVL72 can really help ameliorate that additional communication overhead. NVIDIA is already using NVL72 systems to train Nemotron models efficiently. So NVIDIA released Nemotron 3 Super last month, and this was pre-trained on a GB300 NVL72 system. The Nemotron 3 Super model has 12 billion active parameters, 120 billion total parameters, and it has quite high total number of experts as well as this top K routing factor. So we use 512 experts and a top K factor of 22. And we co-designed a new type of MOE architecture that we call latent MOE, which you can think of as a more extreme design of the granular MOEs that you're already seeing. In particular, the key innovation is that we perform this expert parallel all-to-all communication in a smaller latent space. And this allows us to to train models with even more experts and even higher top K routing factors. And we found in our ablation experiments that this was really useful to produce higher quality models. We also ran some small-scale experiments to measure the impact of using NVL72 instead of the conventional NVL8 system, and we found that pre-training throughput is as much as 70% higher on the NVL72 system. And we expect to co-design future Nematron models to benefit from not only NVL72, but the upcoming NVL576 and NVL1152 systems that are coming on the horizon. And with that, I'll hand back to Pramod.
Thanks, Deepak. So with that, I just wanted to close. This is our Google Cloud, GPU portfolio. So we have, different types of GPUs on Google Cloud, whether you're using like PCIe, low-cost inferencing across all the different ML life cycles, whether also if you're, actually powering high-throughput, low-latency agentic systems all the way up to, A4X with the Vera Rubin platform. So a broad range of portfolio. I also encourage you to visit our AI infrastructure booth. We do have a GB300 rack that we built, so you can explore how the system is put together with the liquid cooling technology. So happy to answer any questions on those systems as well. We also have a G4 rack if you go to the physical AI booth as well. So a lot of hardware for you to explore. And with that, I think thanks for your time again.